this last part of chapter 20, we're going to talk about the idea of what an inductor is and what self-inductance is. Thus far, we've said that if a loop is existing in a changing magnetic field, then it will create a current due to the induced EMF. But what if that current is going through that same coil, and that coil is making a magnetic field so that it is creating a changing magnetic field in a neighboring part of the coil? This is called self-inductance. So what goes on is we start sending external current through a loop of wire that then creates a magnetic field. We can use a right-hand rule to figure out that that direction is going down if the internal current is going that way. And then the neighboring wires will say, hey, I don't like this new magnetic field, and actually the neighboring wires will produce a current in the opposite direction with a magnetic field in the other direction as this magnetic field is being generated from the external current source. So it's very much like the case we talked about last time, where the magnetic field is increasing, that the other magnetic field will want to make a magnetic field in the other direction. And when the external current is turned off, it's going to start producing a magnetic field in the same direction as the external magnetic field was. Even though it's not really external, it's now internal to the device. So this property is called self-inductance, and we can actually measure that in these guys. And these are called inductors because they have self-inductance, and so you can either have a solenoid, or this one is called a toroid when you wrap it around into a donut shape. This self-inductance is given the symbol L, and is basically representing how much EMF we can have for when we're changing a current. So just like resistance and capacitance, L is a proportionality constant for these devices. The negative sign again indicates the current will go in the opposite direction, but we'll use Lenz's law basically to figure out what direction things are going. So basically, the inductor creates an EMF as we are sending current through the inductor. So the inductor's properties are from its physical, the inductance is from its physical properties. It's basically dependent on the area, the length, and the number of turns that we have. And so the inductor symbol is basically just a curly Q. And we're going to draw it in a circuit. So if I can draw it right. And lots of things. So here's another diagram showing the number of things we can do to change the inductance. We can change the number of turns, that would be N. We can change the core material if we have iron or air. So Fe or air are typical core materials. Spacing between the turns, so that's also having to do with the number of turns, is how close they are together. The wire size will affect the inductance as well. The diameter of the coil and the type of winding, whether we have basically, so type of winding. So really the core material, the cross-sectional area, the number of turns are the ones we're going to look at. Mostly are the area and the number of turns. So in here we could put a dielectric constant for the core material, but your book doesn't get that far. So we're just going to stick with the basic properties of the number of turns, the length, and the area. Now we're going to look at an example problem where we'll actually use some of these equations. Here we're looking for the self-inductance, so that's the L value and the EMF during this time interval. And here's some more pictures of inductors so you can kind of get an idea of what the values are. Inductors again are measured in Henry, so here's microhenry. Little U stands for micro typically, nanohenry, so typically pretty small values that we're dealing with for inductors. So these are our two equations with L in it. We got to decide which one we're going to use in this case. So we got to figure out what variables we have. This looks like an N, 300 turns of wire wrapped around a hollow cylinder, so air. I'm not going to get into dealing with other core materials. And a radius, so that's R, and a length, that's a little l. The current increases, so I have a change in current per change in time. So the inductance we're going to get from this formula, because we have the length and we have the N. So we're going to use that formula to find the inductance. So L, we can't use this one because we're trying to find E, So we need L before we get to E. Okay, so L is mu naught times n squared A over the length. Then we have mu naught is again 4 pi times 10 to the negative 7th henries per meter is another form of the units for that. So n is 300 squared, and then the area, we're given the radius, so we're going to use the radius, so pi r squared, 0.019 meters squared for the area, and then divide that all by the length of 6 centimeters, 0.06 meters, gives us a total inductance value of 2.1 times 10 to the negative 3 henries. Then we can use that in the other formula, negative L delta I over delta T, to find out the EMF is negative, so inductance was 0.0021 henries times delta I is 160 minus 20 times 10 to the negative 3 amps, all divided by 7 seconds, gives us 42.7 times 10 to the negative 6 volts, or 42.7 microvolts. So very, very tiny for this particular situation, but we're just dealing with milliamps, so that's not too surprising. So here's all those values again. Now we're going to let you practice with these equations and this idea of an inductor. We're given the inductance this time, so that's our L, and it explicitly says that this is the change in I over change in T. So figure out what formula to use and find the self-induced EMF. So we're looking for E. Okay, hopefully figured out what formula to use. So we're going to use this one because that's the one we have the variables for. We aren't given any information about the number of turns. We're not getting any information about any external magnetic field. So we need to use this equation. So E is equal to negative 0.250 henries times negative 0.2 amps per second. And that gives us 0.05 volts. And then asks us which end of the inductor is at a higher potential. So if current is traveling that way, it's always going to travel to a lower potential. So this is going to be V high and V low.